We're looking at a graph of the relationships between groups of units, which are mathematical objects. Each circle here represents a different group, with lines connecting those with a similar structure. And it's fun to watch this graph expand, but we can also use it to gain insight into these groups of units. First of all, what is a group of units? I think this is best answered with an example, using the group of units mod 12. Here is a multiplication table that represents this group. It's mod 12 because we're doing multiplication mod 12. 5 times 7 is 11 mod 12. This is a group because the multiplication table follows a nice Sudoku rule. Every number appears once in every column and once in every row. And what this really tells us is that if we take all four numbers and multiply them by any single number, we will still have all four numbers as a result. Any multiplication is a one-to-one map, which is a very nice property. And we get that property because these are the units. If we were to use everything mod 12, that would not be true. For example, this row has only zeros and sixes, and this column only has even numbers. It's only the units that give us rows and columns containing everything. So what defines these units? They are co-prime to 12. Okay, so we have these units mod 12, but we could do this with any number. For example, here's the multiplication table for the units mod 8. And we notice it looks very similar. The only difference is that there's 11s on the left and 3s on the right. Other than that, these are the exact same. Because of this, we say that the units mod 12 are isomorphic to the units mod 8. They have the exact same fundamental structure. Let's take a look at another example. Again, with the units mod 12, we'll compare against the units mod 5. Both of these groups have 4 elements. They make a 4x4 multiplication table, but they're not the same. And this is clear if we look at the diagonal. These are all the square numbers, multiplying a number by itself. In the units mod 12, the squares are all the same. But that's not true in the units mod 5. There are 2 different squares. So there is no way we can map between these because the squares act differently. So the units mod 12 are not isomorphic to the units mod 5. But they're not completely different. Let's now introduce the units mod 3. There are only 2 units. We just get a 2x2 multiplication table. And we can kind of embed that structure into the units mod 12 if we ignore 7 and 11. By using just 1 and 5, we get the same structure as U3. So U3 is a subgroup of U12. It's not a true subgroup, but it's isomorphic to a subgroup, so I will use that terminology for the rest of the video. On the right side, we can do the same thing. If we ignore 2 and 3, we're left with a similar structure. So U3 is also a subgroup of U5. U12 and U5 might be different as a whole, but they contain something that is the same. And instead of using multiplication tables, we can also think of this using cycles. For example, U3 is a 2 cycle. We go back and forth between 1 and 2, where these arrows represent multiplying by 2. And similarly, U5 is a 4 cycle, with arrows representing multiplication by 2. And so we can embed U3 within U5 by ignoring 2 and 3. We only go around this cycle 2 arrows at a time. The structure of U12 is 2 separate 2 cycles. And so we can embed U3 by ignoring one of them entirely and just using the other. And thinking of these in cycles makes it a little easier to see the relationships. Let's now look at U15, which is a 2 cycle and a 4 cycle. U5 is a subgroup of U15 because we can ignore that 2 cycle and just use the 4 cycle for the same structure. And U12 is also a subgroup of U15. We just need to ignore the 7 and the 13, and we get 2 separate 2 cycles. And we can do a lot more, but the screen's starting to fill up. So to summarize, U3 is a subgroup of U12 and U5, which are both subgroups of U15. And we can keep adding to this. For example, earlier we saw that U8 is isomorphic to U12. And it turns out that U10 is isomorphic to U5. And U24 contains U8 and U12, but not U5 or U10. And maybe we want to see all of the integers, maybe everything below 100. But that sounds like a lot of work. So let's make the computer do it. Why spend a few hours making a chart if I could spend a few weeks writing a program to do it for me? In order to do this, the program needs 3 steps. First, find the cycles for each modulus. Second, find the relationships between the cycles. And third, graph those relationships. So let's start with the first. I covered this in depth in my previous video, so let's summarize with an example. Let's find the cycles for U68,400. And this is done in 3 steps. First, we split into prime powers. So 68,400 is 16 times 9 times 25 times 19. Next, we multiply each by p minus 1 over p, depending on which prime. Just like this. And finally, we split the power of 2 if possible. The power of 2 was 16, which gave us 8, and will then split into 2 and 4. If this had been 64, we would split off a 2, and we'd be left with 2 and 32. But if this had been 2, we wouldn't be able to split, and it would remain just 2. But in this case, we had 2 and 4. And so then we take these numbers to get the product of a 2 cycle, a 4 cycle, a 6 cycle, a 20 cycle, and an 18 cycle. And for one more example, we first split into prime powers, multiply each by p minus 1 over p, split 2 if possible, and then we get our cycles. So that covers step 1. Now for step 2, to find relationships between the cycles. And so first, let's focus on the question, how do we know if 2 groups are isomorphic? Hey, buddy. You can't stand in front of my mic. Puppy. This might seem clear, like U8 is isomorphic to U12, because each of them is just 2 2 cycles. We just need to check if they have the same representation of cycles. But that doesn't always work. U39 is isomorphic to U35. U39 gives us a 2 and a 12 cycle, but U35 gives us a 4 and a 6 cycle, which appear different, but they're the same, because we can split that 12 cycle into a 3 and 4 cycle, and similarly we can split that 6 cycle into a 2 and 3 cycle. And so this makes things a little bit trickier. Any cycle of order AB can be split into separate A and B cycles, if A and B are co-prime. And so a 2 and a 3 cycle is the same as a 6 cycle, but a 2 and a 2 cycle is not a 4 cycle, and that's why U12 is not U5. So we have these 3 different ways to represent the same structure, but we need to pick one of them, which should be the standard representation. We will use the one on top, because 2 divides 12. We have this divisibility property, and that doesn't hold for the other 2. Neither 4 divides 6 nor 6 divides 4, and neither 2 divides 3 nor 3 divides 2. So only one of these groups has that property, and we can use this in general. Using our example from earlier with U68,400, we found this as a cycle representation, but it's not the standard one. This is the standard representation because 2 divides 2, which divides 2, which divides 12, which divides 180. That does not hold for the top representation. And it turns out this divisibility requirement gives us a unique representation for every group. So let's show this. First, we'll show that this exists. There is some representation that fulfills this divisibility requirement. So how do we find it? Here with this example, we'll split each cycle into its prime powers, and then sort the prime powers left to right, and then we take the product of each column to get our new representation. This sorting of prime powers will always give a result that follows the divisibility rule. And now it's much easier to see that U39 is isomorphic to U35 because they have the same standard representation. Once we've found this standard representation, we can just check directly, do they match? And these unique representations also help us find subgroups. Let's take a look at an example. Earlier, we found this cycle representation. To find the standard representation, we will split into prime powers, reorder, and then take the products. So now at the bottom, we have the standard representation. Now, let's compare this standard representation to 68,400. We see that 60 divides 180, so we can embed a 60 cycle within that 180 cycle. Similarly, 6 divides 12, 2 divides 2, 2 divides 2, and we can kind of just ignore this 2 cycle. And so each of the cycles above are contained within some cycle below, so the group of units above is a subgroup of that below. And this test will work in general to find if something is a subgroup or not. So that completes number 2. We now have a way to find relationships between the cycles. Now let's move to 3, to graph those relationships. The units mod 1 and 2 are trivial, so we'll skip them. And we'll start by randomly placing a circle for U3, which is a 2 cycle. Then we place U4, and it's also a 2 cycle, so these are isomorphic, and we draw a line to link them. Next is U5, which is a 4 cycle. And 2 divides 4, so the 2 cycles are subgroups of the 4 cycle. We'll draw lighter lines to indicate subgroups. Next comes U6, then U7, U8, U9, and U10. Now, it's starting to become messy. It would be nice if related groups were close to each other. So let's make them attract each other. This is worse than before. Let's make all circles repel each other. This is much better. Now we see all the groups that are isomorphic have clumped together. And that means we can remove some of these redundant lines. And we can also simplify the labeling. Now let's add some more groups. Let's look at the groups around the edge, the ones without many connections. These are all primes, 17, 19, and 23. To see this even clearer, let's highlight just the primes. Only the small ones are well connected. The relationships have a lot to do with sharing factors. Let's show just the multiples of 5. They're clumped together. We see the same with the multiples of 7. And more generally, any group will be a subgroup of its multiples. Any UK will be a subgroup of UNK. And this is understandable, but to make it even clearer, we'll notice that if a prime divides UK, its prime power is p to the a, then that same prime power of nk must have an exponent that's at least as big. Which means when we take the step of multiplying by p minus 1 over p, we will end up with a cycle on the left that is a subgroup of a cycle on the right. And this will happen for every prime. Every cycle on the left will be a subgroup of some distinct cycle on the right, which is why above, UK is a subgroup of UNK. So there are always relationships between multiples, but that's not the only thing that causes relationships. Here we see all groups related to U7, which include 13 and 19. Just like 7, they are primes one more than a multiple of 6. The properties of a prime group are really determined by the number 1 below. We also see that U7 is isomorphic to U18. They're both 6 cycles, but for different reasons. U7 is a 6 cycle because 7 minus 1 is 6. But for U18, we split into 2 and 9, and then multiply these each by p minus 1 over p to get the product of a 1 cycle and a 6 cycle. But a 1 cycle is trivial, so we can ignore that. For another example, let's look at the groups related to U11. It's just 11, 22, and those 3 in the middle. But if we add a few more groups, we see that U11 is a subgroup of U25, which is a 20 cycle. 11 and 25 don't inherently seem related, but their unit groups do have a similar structure. How about the groups related to U23? It's just those 3 in the middle. 3, 4, and 6 keep showing up, and they always will. They are subgroups of every group of units above U2. To see why, let's look at that multiplication table for U3. And we want to remember here we're working mod 3. So instead of writing 2, we could write -1. And now this multiplication table also works in mod 4 for U4, and in mod 6 for U6. And it will also work in any mod n, although it won't necessarily be UN, because this is only 2 of the units. But it will be some subgroup of UN for any n that we choose. 1 and -1 always form a subgroup. And so this clump of 3, 4, and 6 is the core of the graph. They are the most connected. But now we may ask, what is the least connected? Some of these primes, 13, 17, and 19, are all by themselves, with no isomorphism. But that's just because we haven't added enough groups. If we continue, we find that 26 is isomorphic to 13. And further adding groups, we also get isomorphisms for 19 and 17 as well. And in general, every prime will have an isomorphism to a different group. And not just the primes. As I showed in my last video, if k is odd, then uk is isomorphic to u2k. And this means that every odd k has an isomorphism, and also that every 2k has an isomorphism. So we might wonder, is there a unit group without an isomorphism? As we just saw, it can't be odd or 2 times something odd, so it must be a multiple of 4. If we return to the graph and look at the circles that are by themselves, 25 is odd, 33 is odd, 23 is odd, but 24 is even, and it's divisible by 4. It's the product of 3 different 2 cycles. And it turns out this does not have an isomorphism. It's the only unit group that is 3 2 cycles. To see why this is the case, let's suppose we want to create a unit group with this structure. For any p that divides our modulus, we'll get a cycle of p minus 1, which means the modulus can only be divisible by 2 and 3. Any larger primes will give a cycle that's too large. Now, if we look at all the powers of 2, anything above 8 has a cycle that's too big, so they won't work. And looking at powers of 3, only 3 will work. Everything above it has a cycle that's too big. So this is all we really have to work with to get a construction that's made of only 2 cycles. And so U24 is the only unit group that is 3 2 cycles. And it's also the largest unit group that is made of entirely 2 cycles. There is no unit group that's the product of 4 2 cycles, or of 5 2 cycles, or any higher number of 2 cycles. And now this raises the question of which constructions of cycles exist as unit groups and which do not. But that's a big question which deserves its own video. For now, I'll leave you with an exercise. Which other moduli under 100 have no isomorphism? We saw this was true for 24, but are there others? Another interesting thing to notice about 24 is that it's the lowest modulus that gives us 3 cycles. And to see that more clearly, let's change the coloring. White for 1 cycle, green for 2 cycles, and yellow for 3 cycles. And now let's add some more groups. We see that 40 also is the product of 3 cycles. It's a 2, a 2, and a 4 cycle. And the same with 48. And now try to predict what's the smallest modulus that has 4 cycles. What do you think? 8 was the smallest with 2. 24 was the smallest with 3. Is there a pattern there? The answer is 120. It has 4 cycles. It's a 2, a 2, a 2, and a 4 cycle. Let's take a look at that in a table. What do you think is the smallest with 5? It is 840. How about 6? This becomes easier to predict if we look at the prime factorization of each number. Each time we just multiply by the next prime. So now do you have a guess? The smallest with 6 cycles is 9,240. It's just 11 times the previous. And this pattern follows. In general, the smallest with n cycles will be 8 times 3 multiplied all the way up to the n minus 1th prime. And we can describe this as being 4 times the n minus 1th primorial. A primorial is like a factorial, but it only uses the primes. So this gives us a pretty good understanding of what are the smallest numbers with n cycles. But this isn't actually true. 8 is not the smallest modulus with a 2-cycle representation. U8 is a 2-cycle times a 2-cycle, but U7 is a 2-cycle times a 3-cycle. But we didn't notice this because the standard representation is a 6-cycle. So U7 can be represented either with 1 or with 2 cycles. Maybe more accurately, 8 is the smallest modulus with a minimum of 2 cycles in its representation. And so this table is not the smallest modulus using that number. It's the smallest using the minimum representation for that number. But we get something different if we use the maximum representation. 7 can be represented with 2 cycles, and 21 can be represented with 3 cycles. And filling in more of this table, we see the values on the right are a lot smaller than that on the left. And we might wonder, is there a way we can predict the next one? Maybe let's look at the prime factorization. They do all include 7, and the lower few include 8, but there doesn't appear to be a pattern. It's not immediately clear what the next one should be. And we'll be even more confused when we do include that next one and see there's a 31 now. The 3 disappeared. So what's going on? The sequence of these numbers, the smallest using the maximum representation, is very interesting, and I'll be diving deeper into that in my next video. So look out for that. In the meantime, if you'd like to interact more with this graph, you can. I made it into a website, which is linked in the description. And there are a lot of options in here to play around. Perhaps my favorite is mouse interference, which lets you push things around.